Hello team. You ready for the last video for the hybridization series? So we've got hybridization schemes, bonding schemes, and now let's do the culmination of it all, the orbital overlap diagrams. So really all this is, and all these are similar. They show the same information, they just represent it in a different way. Right? Like I said, the Lewis structure shows you the bonds and where the electrons go. Vesper structure shows you bond angles, right, and molecular shape. Hybridization scheme shows you how the atomic orbitals blend into hybrids and predicts the Lewis structure. Bonding scheme shows you kind of the Lewis structure and designates what each line is, what orbitals are overlapping, and the designation of those orbitals. So the orbital overlap diagram is the bulkiest, but gives you the most information. It's kind of like a bonding scheme, but we're going to use the Vesper structure because it has to show you we're going to show that instead of lines, we're going to actually draw the orbitals overlapping. So they have to be pointing in the right directions. So it's like a Vesper structure. So we're going to write the Vesper structure, and instead of lines, dashes, and wedges, write the actual orbitals overlapping and designate, right? Draw the orbitals. Right inside each orbital what it is. Is that a sp2 hybrid orbital? Is that an sp3 hybrid orbital? Is it an sp3d2 hybrid orbital? Is it an unhybridized 2pz orbital? Is it an unhybridized 3px orbital, right? We want to draw all that in there to designate it, kind of like what we sort of do with the bonding scheme. And then tell me whether it's sigma or pi. Just write a little sigma next to it or a pi next to it where the electron density is from the overlapping orbitals. I'm not going to do all the examples. We'll do maybe 3 or 4 of them and have at it. You can do these pretty quick, but it's a lot of artwork. So the better at art you are, the better you are. The better you are. The better at art you are, the better you are at orbital overlap diagrams. Ready for some balloon animal little structures? Let's do it. Let's start out easy. Let's start with the NH3. I think I just realized on the bonding scheme video, I did like 5 or 6 examples, and I just kept the number 1 on each one. Oopsie. Who cares? All right. So let's do ammonia. Start simple, and we'll get a little more complicated. Again, you always start with the Lewis structure. Always, always, always. And we got to look at that and go, okay, so that nitrogen is sp3 hybridized, right on, because you got the 4 electron groups. That gives you that's 4 hybrid orbitals, which equates to 4 electron groups. So that's going to be a tetrahedral arrangement of orbitals. So let's draw that. So let's draw the nitrogen atom right there. And we're going to have 4 sp3 hybrid orbitals that look like a tetrahedron, right? So normally that would be a line, line, wedge, dash, right? If we did the Vesper structure. So we're literally drawing the Vesper structure, but draw those orbitals. And these are all sp3 hybrid orbitals. So you draw the orbitals and designate them inside. All right, so now that's going to overlap with 3 hydrogens, and the hydrogen will be the 1s. So let's do that in red. So let's overlap it. See that? So this now, it's hard to draw that in there. We can just go hydrogen 1s right there. Boop, like that. Let's go hydrogen 1s there. And hydrogen 1s there. Ideally, I'd draw that inside, but hydrogens are tiny little things. I'm going to fill in the overlap here. See that black area? That's where the electron density lies. Now that's along the internuclear axis between the hydrogen and the nitrogen, right? So we can get it in there. Let's do this. We can get this in here. Let's do it like this. Let's draw the hydrogen there and the 1s like that. We can do it. Yes, we can. We just have to draw really small. Draw tiny. There we go. And so since that's a head-on overlap, that would be a sigma bond. That would be a sigma bond. And that would be a sigma bond. So you show where the electron density overlap is and tell me whether that's a sigma or pi, right? Sigma head-on overlap, pi side by side, unhybridized p orbital. And so instead of lines, we're actually drawing the orbitals. Now what goes here? That's the lone pair. Do you see that? So let's take our lone pair Pop it right in there. See the lone pair? That's where that baby goes. That is an orbital overlap diagram. That's it. Boy, it shows you a lot of information. It's pretty cool. Let's do a more complicated one. This will be less exciting. Well, it might be more exciting, but this is gonna get really bulky. So there's the AsF4 minus polyatomic ion, which we drew the Lewis structure, which had the expanded octet, if you remember from before, with the negative charge. So let's draw that central arsenic. Let's do that in blue. And we've got 1, 2, 3, 4 single bonds and a lone pair. So that's sp3d. Remember that? So there's sp3d. That's 1, 2, 3, 4, 5 electron groups, which would be a trigonal bipyramid Vesper electron group geometry. So we're going to have one up, one down, one coming this way. This would be the wedge and the dash. Right, so you got the axial and equatorial positions. These are all sp3d hybrid orbitals. So let's draw our sp3d in there. Am I writing small enough for you? There. There's the basic found. Draw the central atom. Draw the hybrid orbitals coming through. 4 of them are fluorines. 1 is a lone pair. So lone pair always goes in equatorial position. So if we did the Vesper structure, that would look like would this be the seesaw molecular shape? But it doesn't matter yet. That's a Vesper structure. We don't have to notate the geometry here. So the lone pair goes there. These are all going to be fluorines. All right. So let's overlap these with the fluorines. Now fluorine has 4 electron groups, 3 lone pairs and a single bond. Those are sp3. So let's draw a fluorine here and draw that. Let's make a better tetrahedron here, because 4 electron groups is going to be a tetrahedron, right? So this might be easier to see here. So I'm going to draw a tetrahedron here. Can you see the tetrahedron of the fluorine? So these would be sp3s. That'll be sp3, and this will be sp3. Let's draw the orbital overlap right there. So that would be the sigma bond right there. See that? That's the head-on overlap between the fluorine sp3 and the arsenic sp3d. This gets bulky, doesn't it? That's just a lone pair. And now let's do the top of the tetrahedron here. So this would be sp3 with the fluorine. So just kind of a tilted sp3, right? Tetrahedron. So this will be sp3, sp3, and sp3. Now what's going to go in these orbitals? Those lone pairs. Do you see that? So we're going to have a lone pair here, lone pair there, lone pair there, lone pairs for everybody. So there's the 3 lone pairs, and then we've got the sigma bond right here. These take a while. I just dislike the terminal halogens. They take forever. Let's do the same thing right here. Let's overlap another fluorine. So this will be kind of an upside down tetrahedron with our sp3s. I'll put sp3 there. And then lone pairs go here, 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 right? There's the 3 lone pairs. And then we've got another overlap with the sigma bond. I'm starting to sweat, man. We got 1 more to go. Oh, I'm going to erase this and make some room. You ready? Now we can draw this. So let's literally do an upside down tetrahedron. Let's make that sp3. Here's the fluorine. Can you see I'm going to leave you a lot of space on your exams for orbital overlap diagrams? You're like, oh, this takes forever. Balloon animal. I told you, I promised you these would look like balloon animals. So that's the top of the tetrahedron. So it's like an upside down tetrahedron. Got our sp3s here. Never said I was a good artist, but I'm trying to do it live so you can follow along with me. Let's put our lone pairs in. And then we've got our head-on overlap right there. We are not doing SF6. No way. But that's an orbital overlap diagram. Shows the 4 sigma bonds, the lone pair, lone pairs, lone pairs, lone pairs. Designates sigma and pi. Whew, I'm sweating. Let's do something else. Well, let's get some pi bonds in here. How about that? So let's do the CH2O we did before. So there's the Lewis structure. We got a double bond we got to count for. So let's head down here. Let's start with that carbon. And that has the 3 electron groups, so that's sp2 hybridized, spp. So let's draw the 3 sp2 hybrids, which looks like a trigonal planar, right? So these are sp2s. I can draw this a little bigger than the crazy one we did last time. All right, so I always start with a central atom and then just draw the hybrid orbitals in the proper electron group geometry, right? So trigonal planars, you can see the 120. I look for those. I look to see you've got the right angles, 120-degree bond angles. So that's going to overlap with a couple of hydrogen atoms down here with their 1s. Let's draw this hydrogen 1s. So we've got our sigma bonds right there. There's the electron density along the internuclear axis. Boom, so that represents that line there. That represents that line there, head-on collision. Now, we've got a sigma and a pi bond here. So let's look at the oxygen, 2 lone pairs and a double bond. That's 3 electron groups, so that's also sp2. So let's draw that. I'll do that in purple. Oh, I fumbled it. No. So let's draw the oxygen. Let's put its sp2 here. I'm going to have to erase this. Welcome to Orbital Overlap Diagrams. There's an sp2. Can you see the 120-degree bond angles as well? So 2 of these are going to be lone pairs. So let's put a lone pair there. So that counts for that lone pair and that lone pair. And then this will be the sigma bond between the carbon and the oxygen right there, head on orbital. So you got some electron density along the internuclear axis. Remember, double bonds look like hot dogs. If you could actually take hot dogs in a bun, right? If you could take a picture of where the electron density is and actually see it, it would literally look like a hot dog. You'd see the hot dog here, and then you're going to have a pi bond with some electron density on either side, which looks like the bun, the top bun and the bottom bun. So you get the hot dog with the top bun, hot dog, bottom bun. So we've got an unhybridized 2p orbital on that carbon, don't we? So since now, do you see where the x-axis, the z-axis is taken up, y's kind of taken up, but the x is open? So let's say the y and the z got hybridized. Let's go ahead and draw, I'll use this color here, an unhybridized 2pz orbital in either direction. I'll use green and whatever that other weird color is. So that is the, so kind of think of it as positive, negative lobes. If you want to, you don't have to do different colors like that. If you want to keep it all the same color so you don't get confused. You could do that as well, because carbon's in n equals 2. This is a 2. Oh, why did I write z? This is x. There we go. So that looks like it's in the x-axis, but you could label the axis anyway. So if you put them both z, who cares? It's just, instead of having it like this, you just go, it's in the x, now it's the z. So there's no right or wrong answer with which ones. But the way this looks, usually the z is up, x is this way, and y is coming out at your face, right? So we're going to have an unhybridized oxygen here, also with a 2pz. Hi, kids, what are you doing? So we've got 2 orbitals, I mean 2 atoms next to each other, both with unhybridized. Why did I write z? I'm obsessed with z. So you see that 2px, 2px? So we're going to get some overlap here. you're going to get some electron density there and there, and that's your pi bond. You see that? That's your pi bond. That's the second line right there. So that's an orbital overlap diagram showing a double bond where you got the electron density here from the sigma and then the pi. Sweet, huh? So the pi is a little weaker than the sigma. The sigma is a stronger one. So a pi bond is not quite as strong. It's so like a double bond isn't quite as double. It's not double the strength of a single bond. You can't. It doesn't like double. So if a single bond is 300 kilojoules per mole, it wouldn't go to 600 because that pi bond, that electron density is not between the nuclei. So it's not quite as strong. There you go. Let's do one more. Can you get this one on your own? Let's do it. Let's do the C2H2, kind of resurrecting the ones we did before. And on an exam, I could ask you anything. I could ask you for the hybridization scheme, or the bonding scheme, or the orbital overlap diagram, or the Vesper structure, or the Lewis structure, right? The Lewis structure, Vesper structure, hybridization scheme, bonding scheme, orbital overlap diagram. So I've had people where I asked for, say, a hybridization scheme, and they gave me a perfect bonding scheme, and I had to give them 0. Because you did the wrong problem perfectly. No! So make sure you understand what I'm asking for. If I'm asking for a bonding scheme, give me a bonding scheme, not a hybridization scheme. It happens every time. I was like, oh, there's always a couple students like, it just breaks my heart. I want to see you guys do well. You're my academic children. You're my team. I want to see you prosper and flourish. Here we go. Shut up, blocks. Let's do this. All right, you ready? So let's draw carbon number 1. Let's look at the hybridization. 1, 2 electron groups, so that's sp. So you're going to get a linear relation between these. There's your sp. And your sp, you're going to have a hydrogen overlapping over here. So let's overlap that hydrogen here with the 1s. And we've got a sigma bond right there. Easy. Probably look, it's kind of a mirror image on the other side. So the second carbon, let's do that, say in purple, will also be sp hybridized, 2 electron groups. So let's do the same thing. Let's draw the sp there and the sp there. They look exactly the same. Head-on overlap, crash, crash, crash. There's our sigma bond. The other 2 will be pi bonds. So we got 2 pi bonds to worry about here. We got another hydrogen on the other side with head-on overlap, right? Electron density along the internuclear axis. That is a sigma. So you can see that whole linear shape developing here. But what makes this bond so strong, that triple bond? You got 2 pi bonds. Well, it looks like the x-axis is taken up. So let's say the px, we took the s and the px and hybridized those. That means we're going to have a pz. I keep wanting to do pz, so let's do pz. I'll do that in green. So this carbon will have a 2pz. Green's not showing up. Come on, baby, give me one more. This carbon will also have an unhybridized 2pz. Yeah, I know. You hungry, buddy? So we've got some electron density there, right? There's our first pi bond. So we used up the px and the hybrid orbitals. We got 2 adjacent unhybrid, and obviously they'd be overlapping. This spreads it out. So these would be really close and those would overlap. I'm just spreading it out so we can write stuff. But in real life, those are right next to each other. We've got the py orbitals we haven't used yet. So the 2pz were unhybridized. The px were hybridized. So let's do this in this off color. So now I can't have these coming at your face because really the py's are literally coming at your face like that. You can't draw that. So usually we angle them off. So let's say we've got the 2 py's. The unhybridized 2py there, and an unhybridized 2py there. So now we have another pi bond. So we could call this like pi 1, boop, And then this would be right there, pi 2, the third line. So there's a lot of electron density shared between these two atoms, some along the internuclear axis. You got some up above the axis and some coming out at you this way. Craziness, yeah. That's orbital overlap diagrams. They're not terribly challenging. They're just bulky and they take a long time to draw. So the better your artist work, the better they look. But just make sure you don't leave a lobe with no designation. There's got to be a designation in there. And tell me where the overlap is and whether that's sigma in between the nuclei or pi above and below. Hybridization's done. Woo woo!